The last topic we're going to address in this semester is quantum physics. Through this section, we're going to look at a few different aspects of the basics of quantum physics. We're not going in very deep, just some of the basics. So we'll be doing that over the next few videos. In this video, we're going to look at early quantum theory, stuff that was hinting at quantum physics, but it wasn't fully recognized quite yet at this point. So we start off by looking at the cathode ray tube. Now, we talked a little bit about the cathode ray tube back in our discussion about electricity and magnetism. Basically, what we have is a cathode, which is hooked up to a negative charge, so this is negatively charged, and then an anode, which is a positively charged plate because it's connected to the positive side of a high voltage. And that causes any electrons to go shooting across, accelerating away from the negative plate but towards the positive plate, and it causes it to hit the glass, and it causes the glass to glow a little bit. Now, in the late 19th century, when this was discovered, they didn't really know what was causing it to glow. They didn't know there was such thing as a particle of an electron. So they just called these cathode rays because they came from the negative charge, or the cathode side of a voltage, and it seemed like it was creating these random rays, light rays, coming from the cathode. So, cathode ray tube. Perhaps you remember those big box monitors for computers and TVs. They were just big boxes. They weren't flat screens, they were big boxes. That's because those were cathode ray tube TVs. The way that they worked is they would produce electrons, which would then be repelled by the negative plate, attracted to the positive plate, and then they would shoot through. And then due to either electric fields or magnetic fields, in this case it would be going into the page, so let me draw it that way. A magnetic field going into the page. Because of those fields, it creates a force on the electrons, causing them to deflect one way or another. And so you can adjust where the cathode ray, where it hits the glass, based on the electric and magnetic fields. And so that's what those big cathode ray tube, or CRT monitors, that's how they worked. Varying electric and magnetic fields that would distort the path of electrons. Great. Okay, so I kind of fast forwarded into the, late 20th century there for a second, but let's get back to the late 19th century, the late 1800s. We could see all of this happening. We saw this cathode ray tube. We knew we could deflect it with electric and magnetic fields. But what were these things? What were these cathode rays? We didn't know for sure. Well, one thing we could tell from that is we could tell that they had some sort of a mass. And here's what I mean. Recall from our discussion on uniform circular motion in Physics 1 that the centripetal force is going to equal mass times acceleration, but your centripetal acceleration is v squared over r. Okay. Well, in this case, you have a centripetal force caused by either an electric field or a magnetic field. Let's take the magnetic field. So there's the centripetal force, our magnetic force, we'll say, and that has to equal the centripetal mass times centripetal acceleration, v squared over r. If we rearrange this a little bit, we get a ratio of charge to mass. That's going to be v over br. Alright, now let's apply this to this specific situation, and we apply this to an electron. It's some sort of a ray moving at the speed of light, and so we know that the speed of light is the electric field divided by the magnetic field. And so then we get an equation that looks like this. The ratio of the electron's charge to the electron's mass is going to equal the electric field divided by the magnetic field squared times the radius. And that's going to be a constant number. It's going to be a constant number. So what we find is that the ratio of an electron's charge to its mass is this number, 1.76 times 10 to the 11th. You don't need to remember this number. It's nothing special, nothing fancy. But what it tells us is that when an electron does have charge, it has to have mass as well, and those two are proportional to each other somehow. That's all they could tell in the late 19th century. Shortly after that, also late 1800s, a scientist by the name of Millikan devised a cool experiment to actually find the mass of an electron. Here's what he did. He had a plate where he charged it so that it produced an electric field, like so, from the positive plate to the negative plate. And he used an atomizer to create oil droplets that would then come through this hole and then would be suspended in the middle of these two plates. They would just float. Now he found that he had to have a particular electric field to do this. Well, that's okay because it actually helps us. Because we know that these droplets have a weight, and that's what's pulling them downward. But these negative charges, these droplets of oil have a negative charge, and so the downward electric field, remember that never mind, I've got this already here. The electric field is going to be the electric force is going to be the charge times the electric field. Charges are negative, so the force is going to be pointing upwards opposite the electric field. And so he would just adjust the electric field until these two balance, and you end up having that the electric field has to equal the force of gravity, or that QE has to equal mg. Okay, so what he does is he sets the electric field. G is just a constant, we know that, so that's done. So he sets the electric field, and then he measures the mass of these oil droplets after the experiment is done. And so he's got a set of electric fields, masses, and then he can just, in just a simple lab experiment similar to what we do in our labs, he can create a plot and comes out with a particular charge for that given mass. And then if he does a plot of, say, charge to mass, no, sorry, let me do it this way. Electric field here and then mass here. Then you end up getting a slope, and that slope would be your charge Q. However it was he found it, because of this experiment, he could easily find the charge of each oil droplet and thus determine from this ratio back here, using this ratio here, he was able to find the charge of one single electron, which is pretty cool. Pretty cool that they could do that with oil droplets suspended in an electric field. And so Millikan found that the charge of an electron was somewhere around 1.5 times 10 to the minus 19th coulombs. We know now it's 1.602. We've got a more accurate number today. And then knowing that, we could use that ratio to find the mass of an electron, which is 9.11 times 10 to the 31st kilograms. Oh, something else I need to say that's important. All of this data that he gets using this lab setup, he found that every single charge in these oil droplets was a multiple of this electron value. So any charge Q is some whole number multiple of E. And that tells us that the reason we have charge is due to extra or lacking electrons. It's because of the electrons that we have charge. Okay, fast forward a few more years, we started coming up with this weird experiment, weird result that we had. We were looking at objects that emit radiation, objects such as the sun, other stars, light bulbs. Their total intensity was proportional to the fourth power of their temperature. In other words, the intensity is proportional to temperature to the fourth power. And we call this thermal radiation. And we have these black bodies. A black body is an object that only emits thermal radiation. It doesn't lose energy anyway at all. In other words, we call these perfect absorbers and perfect emitters. That's not really the point we want to get to. The point we want to get is that this caused some issues when it came back to the charge of electrons and this early quantum theory stuff. Some of the experiments they had showed some very, very distinct values from this chart you see on the right, but couldn't be explained using the current understanding of thermal radiation. And so a few years later came a man named Max Planck, and in the next video we'll talk a little bit more about Max Planck and what it was that he did that introduced the field of quantum physics.